Okay, so here's another exercise directly out of the Mike and Ike textbook. This is exercise 2.3, the matrix representation of operator products. So we talked about what happens when we have two operators, B and A. And this is just a quick reminder of some things that we've covered. A is a linear operator. That means is A applied to a whole vector is the same thing as applying A to all the various pieces of that vector. Another thing that we've covered is A can be represented in matrix form. This is the notation AJI in some other basis W. And then in the same way, these are all just letters. So we can find some other operator B acting on WJ that has its own matrix representation. Let's call it BKJ, operating on this new basis X. And so the question being posed to us is, suppose that A is a linear operator from vector space V to vector space W, and B is a linear operator from vector space W to vector space X, and also further suppose that these little VI vectors are a basis for V, WJ vectors are a basis for W, and XK vectors are a basis for X. So we have a linear operator A from V to W, a linear operator B from W to X, and there are, each of these vector spaces has a different set of basis vectors. So we want to show that the operator BA being applied to some vector VI is equivalent to, has some matrix representation, looks like this, BI, KI. BI sub KI, we'll get to it. Okay, so just starting with the fact that, let's just start with this first property here, that we know A is a linear operator. And so forgive me if I rely on my notes here. So BA being applied to VI, right? You could imagine, just putting some parentheses around this, right? So I could just imagine putting some parentheses around this part. And so that is equal to B I, call it AI with A being applied to V sub J, V sub I, right? Being applied to V sub I, like this. And I could further write that as B operating on this AJI, acting on WJ, right? So I've just taken A on VI and turn it into this AJI notation here. Well, if I could do that with A, well, AJI, that's just a constant, it's just a number now, right? It just represents some entry in a matrix. And so if I could do that, I could do the same thing with B. And so let me pull this B right here, right? So I'll just rewrite this. I will just rewrite this as, the sum I, A, J, I, where J is the row and I is the column that's in question. I believe this is a sum over J. Yeah, this is a sum over J here. Okay. And then we apply this B operator to some basis vector WJ. Well, once more, let me put some suggested parentheses just around this part right here. B operating on W sub J. Well, that's just this right here, right? And so we can rewrite this further as J A J I, and then take the sum over K. Let me put a K right there. Sum over K of B kj acting on vector basis vector xk in our new basis, right? And just to make things easier, I'm gonna move all of my sums to. I'm gonna group my sums together like this. J k, then A J I times B kj. And because these are just constants, I'll actually switch these around. Again, just to make it a little more suggestive in the notation. A J I. All of that being applied to x sub k. And so if I just go ahead and take the sum, so I see I have a j here and j here. So if I just take, and also take the notation, let's say BA, I don't know, MN, I'm going to use that to mean something like BMN, BM and AN, something like that, right? So if we just, because there is a J term for both of these, I'm just going to clean this up just a little bit more and get rid of this J subscript. So that's going to equal K, B, A, subscript Ki, all acting on the X vector, the X basis vector for the X basis. And when we take all of that together, we get that BA operating on this operate on this vector, is the exact same as, has a matrix representation here. So show that BA applied to that equals that. There you go. Easy? Maybe.